Tonight, we're going to go on a journey together, exploring the past year of my life, designing, manufacturing, and flying my two-stage model rocket, V2 Sierra. Let's go. Let's talk about the goals of this project. First, to do my own model rocket airframe design from scratch. I used to fly Estes kits as a kid, and sometimes I would modify them, but I took a 15-year break from flying rockets and never designed my own before. The second objective was to design a flight computer that will control the rocket flight functions, like connecting to sensors and using this data to do live analysis in order to determine what stage of flight the rocket is currently in. Based on this state machine, the computer will then air start a second motor if certain safety parameters are met, deploy parachutes, all while recording in 4K and live streaming time series data to a base station connected to my laptop on the ground. The original time series data rate goal was 10 Hz, or 10 data points per second. The next goal was to design my own PCB with all SMD components, except for the MCUs, because I had killed two RP2040s last year, and I was scared that if I did this to an SMD RP2040, that could be a really bad day in the field instead of being able to just go into my toolbox and grab another one of these and continue on. And lastly, to have as close as possible to 100% unit test coverage for my code that runs automatically every time I push new code to the repo. And the main goal of this project was to just try new things and learn through doing. Have fun, launch some rockets, and hopefully get them back in the same shape that they left in.
This is horribly broken.
Before we get into it, I want to talk a little bit about motivation, goals, and picking deadlines before you start your project. For me, I know that deadlines and pressure increase my productivity. This has also been shown by several psychological studies that the more pressure you have increases your productivity to a point, and then you have a meltdown, like I did in college. For me, I find that this pressure increases my productivity, even if the deadlines are arbitrary. Also, I found many years ago that having an accountability buddy, like one of your friends that doesn't really do anything for the project, but just is willing to sit around and listen to you ramble about your progress for 20 minutes every week, but you tell yourself that they're holding you accountable and you can't let them down. This is really helpful. Your mind is a powerful thing and you can make it valuable. So, in November of 2024, when I started planning for this project, I started by picking the launch date, which would be the first weekend in May. And then I would do everything in my power to not change this date.
Oh, wow. I didn't start recording because I thought you were going to count down.
I spent the entire month of November to December doing PCB design. I was still working a full-time job at this time, so I would come home every night at 6 o'clock and then start working. I would work from that time until 1 or 2 o'clock in the morning every single day for this month. I've had a lot of success with complete immersion in the past when you're trying to learn a new technical skill or complete a big project. I think that just dedicating every bit of your free time and energy into a project is the best way to get through it. This project, like every project, has good design decisions and bad design decisions. And we're always limited by what we don't know. Something that was important to me when I started doing this project was that I had ideas on how some things could work, and I really wanted to try to explore those ideas and just see if I could do it rather than spending a bunch of time researching the most optimal or industry standard way of doing something and then trying to recreate that. Because I find that when I do that, I'll spend a ton of time going down this rabbit hole of reading books, reading blogs, watching YouTube videos, and then I won't really do anything. And it was more important to me to finish the project and have something that would work. And if I was going to use this project for something like a portfolio or resume, I think that it's actually more important to be able to explain all of your design decisions and know the thinking of why you did it and how everything works rather than just kind of using ChatGPT or copying something you found online and having pretty much no clue what's actually happening under the hood. Right when I started, the biggest constraint was my knowledge. I knew that I wanted to do a PCB for this project because I had heard a beep. I wanted to do a PCB for this project because I've only done things like proto boards before, And all of those projects generally have a lot of issues with shorts, just really weird electrical stuff going on. And if you need to make more than one board, it just takes forever and the results are really all over the place. Designing this rocket, there's a surprising number of decisions that you have to make, like how long the rocket should be, what fin shape to use, how the fins are constructed, and most importantly, how everything ties together into a structure that's both strong, stable, and serviceable. Up until this point, my experience in model rocketry was building or modifying existing kits, which is very different from starting with a blank sheet of paper and trying to design a two-stage rocket that needs to be stable both with the booster attached and as a sustainer flying on its own. At the start, I honestly didn't know how to answer some very basic questions like how to size components or how the aerodynamics of a rocket even work. Where I started was with this book called The Model Rocketry Handbook by Harry Stein and Bill Stein. The book is an excellent resource. It covers almost all the fundamentals you need to safely get started in model rocketry and high power rocketry design. The chapters I found most helpful were the aerodynamics of model rockets, why fillets are more important than you might think, proper fin construction and how to use fin jigs, and most importantly, for this project, how to approach the design of a two-stage rocket. Beyond this book, a huge part of my learning came from the online rocketry community itself. BPS Space was a massive inspiration. Joe's work really pushed me to take this project further, and honestly, it's a big reason that I decided to document the process at all. Thanks, Joe. And the guys from the Anti-Gravity group. They have a lot of neat podcasts that I've gotten a lot of little gold nuggets from and learned a lot. And Alex from Pittsburgh Space Command, who helped me do my L1 certification. With this new knowledge in hand, I started working in OpenRocket to design the airframe in a very rough sense before heading into SolidWorks to actually begin the mechanical design. OpenRocket is an open source rocketry flight simulation and design tool. It helps you quickly design a rocket's geometry, materials, and motors, and then simulate flights to see things like stability margin, altitude, velocity, and accelerations. As soon as I started laying out the model rocket, even with only a rough idea of the PCB size, shape, and battery choice, I realized that this was going to be a very heavy rocket relative to the lifting power that you can get with a low power rocket motor. This forced a number of compromises to ensure that the rocket could safely leave the pad. Compounding this, when I'd started this design, I had only ever flown Estes motors, so in my mind, rocket motors basically topped out around an F-15. Hey, we're almost halfway done. Woo! Additionally, with the chunky batteries that I'd spec'd, this rocket comes to almost 900 grams fully loaded with paint, glue, hot sauce, and recovery gear. This was a very long way of saying that the rocket is really heavy, and the motors that I could buy at the time are relatively low power. So my only choice was to try and make the rocket as light as possible. The main issue is not that you can't get an F motor to lift this rocket off the pad, but you need to have the rocket traveling fast enough at the end of the launch rail that the fins can actually do anything. Rocket fins work by generating aerodynamic restoring forces. When airflow hits them at an angle, they produce lift that pushes the rocket back towards a stable and hopefully upright orientation. This is very similar to how a rudder on a boat also has a minimum speed where the rudder can maintain control authority of the vehicle. A good analogy is sticking your hand out the window of a moving car. When you rotate your wrist, you change the angle between your hand and the airflow, creating a force and a torque that tries to move your hand up or down relative to whichever way you've rotated it. Passively stabilized rockets like this one use symmetric fins to control pitch and yaw. Roll is usually not well controlled. Passively stabilized rockets often spin to fairly high roll rates due to small fin misalignments. Once you have your rocket's mass, and it's modeled fairly accurately in OpenRocket, you need to make a few assumptions, and then other things become a fairly deterministic physics equation, with small tweaks along the way. I had access to a 40-inch long, quarter-inch launch rod. There's a lot of options online, but I decided that a safe target to reach was about 40 feet per second at the end of the launch rod. That rod exit velocity became my primary design constraint. There's a lot of different rocket motors out there with different thrust curves. Some rockets are really punchy right off the bottom that have a very high impulse over a very short burn period, and some rockets actually have a much longer burn with a lower average thrust. What I went with for this was the Intertech F52 motor for the lower stage, the booster, and then for the upper stage, I went with the Estes E16-4. I went with a much lower powered upper stage motor because the whole point behind this rocket is not to go as fast or far as possible, but I just want to do a two-stage rocket. I want to prove that I can do it. Can I design a flight computer that can record video, record data, can it ignite the second motor in the air, and then can I get everything back again? Now, on to the mechanical design for this project. This is actually my favorite part. I love mechanical design. I think that doing CAD is like playing an extremely slow-paced video game. So I tried to make the sled that all of the avionics sit on as light as possible by adding all of these pockets and lightning holes through them. And it's actually pretty flexible in bending, but everything really stiffens up a lot once you bolt on the nose cone, which is modeled as two pieces and then bonded together after for ease of printing. It's only 2 walls thick, so with a 0.4 millimeter nozzle, this ends up having a wall thickness of 0.8 millimeters for this skin. And then the camera sits underneath this bulkhead. And that's another really awful design decision that I wish I could take back. I've tried to make use of this transition period to get a better angle, to get this camera aimed down so that we could see the fins when the rocket flies. But the problem is that underneath this bottom bulkhead is a pressurized zone that you pressurize with a pyrotechnic charge to get the nose cone off to deploy the parachutes. And you have this sensitive camera with these flames and high pressure and lines that are getting pulled taut when the nose cone deploys. It's really not a good choice, but it was a constraint that I couldn't work around any better than this at the time. And then we come down to the motor mounts. I designed them in a bunch of different pieces, and they all bond together. Another issue is that I wish I had done through wall fins on the upper section of this rocket. I had just been learning about them at the time that I was doing this design. I was just learning about their importance, and I somewhat implemented it on the lower section, but I didn't tie it through all the way. So the lower fin cam for the booster is actually pretty strong. It's very stiff, but the upper section just has fins that are CA glued on. I have broken several of these just in transport or when this rocket had a hard landing before. Also, one more note about the fin cams on the lower, the through-wall fin cams, the through-wall fins. It also makes it so much easier for aligning the fins. You don't even need a fin jig, which I did use a fin jig to align them, but you don't even need a fin jig if you have them slot into a 3D printed recess for them. So, tip out there for you guys. Keep that one. Then, as we travel up to the avionics bay, which I'm particularly proud of, the V2.1 rocket board is 2.9 inches wide, and with the wires installed in the screw terminals, the clearance is just perfect as you install the nose cone. Okay, let's talk about some good and bad design decisions. The motor mounts ended up being strong and very easy to work with. I'm really happy that I used connectors like the JST PH and SH line for ease of swapping boards and components. The magnetic connectors that I used to connect to a remote temperature sensor and also to a deployment check switch ended up being pretty bad. They were not strong enough. They fell apart multiple times in different ways. Sometimes you would put the nose cone together and get everything ready and prepped, put it on the launch pad, and they would just come apart sitting there so the rocket wouldn't arm, it wouldn't pass the pre-flight check. Had no idea what was going on, had to stop, take apart the entire rocket. Another bad design decision was using these 8 M2 bolts to hold the AV bay on to the rest of the rocket. These are tiny, and when you're standing in a field trying to operate a tiny little wrench to take things apart, they're flying all over the place, and the walls are really thin. It takes too much time to try and operate these. And one of the worst things, one of the worst design decisions about this rocket that I just wasn't aware of at the time is you need to be able to arm your pyro charges while the rocket is in as safe as a position as possible, on the rail, pointed up. But this pyro arming switch is inside that nose cone, and it's just a slide switch that's on the PCB. So that means to prep this rocket to be ready to go, I have to arm that switch with everything open, with the PCB exposed, and then I have to carefully and quickly put in these 8 M2 bolts, all while having this rocket just sitting on a table in front of me, and then I have to carefully run over to the launch stand, put it on there. Really dangerous. It's always a scary moment when your code is in control of the pyros. Not a good choice. Luckily, I already fixed that in the next version of this design, which uses screw switches that you can access with a screwdriver through the outer wall of the rocket while it's on the launch pad. Much safer position to be in. Okay, batteries. The system idles at 400 milliamps and draws about 600 milliamps during flight. My requirements specify up to 6 hours of idle time followed by 10 minutes of runtime, even though the actual flight should only be about 60 seconds. At a nominal system voltage of approximately 7 volts, this corresponds to a total energy requirement of roughly 18 watt-hours, including some margin. Based on these requirements, I selected two 18650 lithium-ion cells in series, providing a nominal voltage of 7.4 volts. Assuming the cells are around the 3.5 amp hour range, this configuration delivers approximately 21 to 26 watt hours of energy, which reasonably satisfies my original requirements. Cheap components from Amazon. Don't buy electronic components from Amazon. Buy them from DigiKey or Mouser or someplace that sells higher quality components. On this rocket, every component except one was not from Amazon. This is some foreshadowing here. This single component caused a failure on the first flight of this rocket. The one part I bought from Amazon was this battery box, which I modified, replacing the 28 gauge wire with 20 gauge wire and hot glued everything together. This is a great segue to the first launch, but first, let's talk about pyro channels and code. This board has 3 pyro channels. Technically 4, as the same low-side MOSFET is used to provide the camera with power. Channel 0 is wired to a firewire in a 1 gram black powder charge mounted to the underside of the AV sled bulkhead. It sits in a 3D printed cup, and in testing, I found that it was completely sufficient for my use case to just fill the cup with black powder and hot glue a lid on the top. There are a few black powder calculators online that you can use, but with my rocketry friend, we just tested a bunch of different values and 1 gram seemed about right. Thanks, Fletcher, for all the help and letting me set off all these bombs in your backyard. The second pyro channel is wired to the second stage motor, and a third is used as a backup pyro channel for the main chute in case the first pyro channel fails. Redundancy is a big thing in aerospace, and you should expect and plan for failures. I'm going to be going into detail on the code architecture for the rocket board video, but here we're just going to stop and talk about a couple of the safety features and the code that governs the second stage ignition. This is a 2-stage rocket. After the first stage burns, we assess if it's safe to ignite the second stage. Then we air start the second motor with a firewire that is plumbed through the rocket airframe. After the first stage has burned and we begin the stage 1 coast, the most important thing we care about in deciding if we should ignite the second stage is where the rocket is pointing. You can imagine that if the rocket is pointing in any direction besides almost straight up, it's not likely to be safe to continue, and the flight should be immediately aborted. What does it mean to abort? It means that we do not ignite the second stage. It means that we just pop this parachute pyro charge, aborting the flight, trying our best to get the parachute out to salvage the rocket, and hopefully minimize any other damage to anything else that the rocket could be heading towards because it's not going up. The first flight was an absolute mess. Remember, when I started this project, I said that I was going to launch May 1st, and I would do everything in my power to not change that date. I meant this, I didn't change it, but everything else fell apart. The entire event was scheduled into only 4 days, with 2 days to do the entire mechanical build of 2 rockets, modifying the base station, 1 day for testing, and then the launch day. It was a big sloppy mess.
Is that what you expect?
No. That's great that GPS is online, but why is it not going to the next state? I flew to my friend's house in Pittsburgh, Pennsylvania to do the build and launch because I live in Manhattan and it's kind of impossible to launch a rocket anywhere nearby here. My friend Fletcher was nice enough to let me stay at his house and even build his own V2 rocket following my design. The mech build went long and we had almost no time for integration testing. We didn't have full unit test coverage at the time, and I was still changing the code the night before and honestly the morning before the launch, making some horrifying mistakes. Like, I accidentally deleted the line of code that updates the flight states the night before the launch. Then, the morning of the launch, I woke up extremely early to do one last integration test before packing everything up. And of course, the rocket wouldn't change state, and it took me like 3 hours of sitting there trying to figure out how to resolve this. We eventually got to the launch location halfway through the day, where we were greeted by gusts of winds up to 27 miles per hour. We decided that it would only be safe to fly the upper stage on the E16-4 motor from Estes and just do motor ejection, with the pyro charges deactivated because the code was so rushed and buggy at this state. I had no confidence that the recovery code wouldn't try and deploy the parachute on the launch pad, or not at all. The day started with sending a test rocket into a tree, and then we had to pack up everything and move to the other corner of the field to try again from over there.
There we go, baby. Uh-oh, it's going towards the trees.
Nothing worked. There were random bugs ranging from the base station and rocket board state machines going out of sync to the GPS refusing to get a fix, and then dropped radio packets. This was all made so stressful by the high winds blowing our tools around, the stupid 8 M2 bolts we had to remove a bunch of times, power cycling the rocket, and we did everything we could. We were working furiously. We were just literally changing the code on the field, doing everything we could to get this rocket to fly. And then the sun crested behind the trees, and I just shut my laptop. Without saying a single word, we just got up, started packing up the base camp. The sun went down. It was brutal. Brutal silence. We packed up everything, we got in the van, and we left. But I wanted a second chance. Bad. And I wasn't going to give up. Fast forward 1 month later to June, and we're back in the same field. Again, pretty bad conditions. Low cloud cover, gusty high-speed winds. We decided that it would be safer to just launch a single-stage rocket again. Fletcher's rocket kept rebooting because of some software bug that restarts the rocket board if it doesn't get a GPS fix within 3 minutes. So, we decided to launch it anyways. This would still be a useful test, giving me valuable information on how the airframe holds up in flight and how stable it is.
Damn.
We forgot to tie on the launch cord to the avionics bay. We were surprisingly able to recover everything, and the rocket was still in pretty good shape. Fast forward to the next day, when it was time to launch my rocket, the Sierra V2. Once again, I decided to launch this as a single stage, just flying on this E16 motor because of the gusty winds. And then, to make it even better, it started raining.
3, 2, 1, 0. Yes! Uh-oh. No! Ah!
Alright, a lot of emotions going on there, but obviously we can see the problem, is that the parachute did deploy, but it didn't open all the way. I've seen lots of different ways of folding and packing parachutes online. This one has worked for me in the past, but unfortunately not this day. Luckily, the apogee was pretty low, and there was really no damage to any mechanical component, except for the one electrical component I bought on Amazon, which was that cheap battery box. As soon as I popped open the avionics bay, I found that the batteries were literally loose, clonking around in there, and everything was off, obviously. I plugged the computer in to see if there was any time series or video data. No time series data, which is weird. And most upsettingly, there was no video data. I thought there would be at least something like the start of the flight, because I had done tests before removing power, and there's usually some data loss, but you get some video. It actually took me 5 or 6 months to figure out what went wrong. And I'm going to let you guys guess. What do you think it was? No SD card? Wrong SD card? System brownout? Or my code turned the camera off during flight? If you guessed all of these, you're right. I flew this rocket several times in 2025, and every single one of these reasons accounted for me not getting video footage from one of these flights. Let's fast forward a few months. After June, I had a lot of time to overhaul the code that governs the flight mode and do a lot of testing. Honestly, the May launch was too aggressive of a deadline. I was killing myself, working every minute for 5 months straight, and I just wasn't ready. So I took a few weeks off and went into the ocean for the first time ever, and then I got back to it. From July to August, I focused on getting my high-power rocketry level 1 certificate. I decided to apply a 4-inch modified lock kit using my flight computer as a passenger, and I succeeded, which was great. However, my rocket board still got no video. Very sad. But we're supposed to be talking about the November V2 launch. So let's fast forward to November. At this launch, I was again joined by my good friend Fletcher with his V2. We decided to launch his first again.
3, 2, 1.
So, obviously that did not go to plan.
Yeah.
The launch lug sheared off immediately as the rocket began its liftoff. From earlier, we established that passively stabilized rockets need to be traveling at a minimum speed for the fins to work. This didn't happen. After the rocket motor ignites, it pitched over hard, and you can't see it from this video, but we almost sent this rocket through a house. And we're really lucky it went away from us. The good news, though, is that the code worked. The angle off vertical was too great, and the rocket attempted to abort the flight and pop the main parachute instead of igniting the second stage motor. But still no time series data, and no video. There were 2 major takeaways and an upgrade as a result of this launch. First, I did something that for some reason I was never able to do. Before. I read the manual for the RunCam Split 4 and found that it requires a U3 128GB micro SD card formatted as exFAT. I had been putting random SD cards into the camera this entire time with random formats and write speeds. Secondly, the launch lug, which was attached only to the sustainer so that it could be flown as a single stage, was not a through-wall component. It was only bonded to the outside of the tube using CA glue. After a quick redesign and a little rocket surgery, I was confident that we were not going to have the same mistake again. December, the last chance to finish this project in 2025. If I didn't succeed with this attempt, I was going to have to leave my tribe and wander off into the jungle, alone. Everything was riding on this. It was a big moment, and it worked. Everything worked. It was a very emotional day. It was -2 degrees Celsius or 28 degrees Fahrenheit, with freezing wind gusts up to 14 miles per hour. These are pretty terrible conditions for a launch day. The wind chill was so bad that after a few minutes of your hands being out of your gloves, they would turn red and go numb, making it almost impossible to articulate the 8 M2 bolts needed to assemble the AV bay. But through a mixture of luck, better preparation, testing, and whey protein powder, everything just barely worked.
2, 1, go! Woo! Oh, yes! The second stage is going! Yes! Come on, pop that parachute! Parachute's out! Dude!
Oh, I think it's gonna land.
We did it! We did it! Yes! 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 My God! Oh, that feels so good!
So, I know that you have a few questions. First, what did the time series data look like? Bad. Okay, next topic. Why does the onboard video end at apogee? I was also confused about this, because when I found the rocket, it was on and idling. But right after the V2 launch, I actually launched the L1 rocket and the same thing happened. So after the launch, I dug further and I found another clue. The time series data stored on board the rocket also stops right at apogee. This makes me think it was a brownout, potentially influenced by the extreme cold that day. Batteries don't like cold, and they're more likely to brown out in cold temperatures. I did try to recreate these results in my apartment, but it was a much warmer day. So I put the rocket board into the freezer to cool it down a little bit around -6 degrees Celsius or 20 degrees Fahrenheit, which is approximately the temperature that day. I ran 2 tests using some Pyro test code I had written before, and I used the L1 avionics bay, which is the same computer, just a different avionics bay. For both of them, I wired a FireWire to the first Pyro channel, so there's no black powder charge here, just the FireWire, because I'm going to be doing all of this testing on my balcony in the East Village. So for the first test, we just count down and ignite the FireWire.
3, 2, 1, now. Oh, that was exciting.
The second test is much more representative of an actual flight. It's actually just running the flight code. So we go through the full pre-flight check where we get a GPS fix, all the sensors are running and recording data, and then I simulate the launch event by lifting up the AV bay, the cameras are running, and then at apogee, the FireWire goes off. Oddly enough, everything worked here. Like we have all the onboard video, the system did not run out. It was a little bit warmer, even though it's still extremely cold in Manhattan in December, but everything worked. Whatever. Weird. But still, the December launch was an amazing success.
With this project, I hit or exceeded all of the original goals that I set out to do, and I almost killed myself doing it, figuratively and literally. And my friends who joined me, they almost died too. But I'm so grateful because even though this was brutal, it was an extremely challenging success story. It worked, and I have to thank all of my friends and coworkers who dedicated their time and their attention along the way to make this a real thing. And I'm so proud of this, and I'm so glad that I stuck with it. Someone told me something along the way, which I don't think was a compliment, but I'm choosing to take it that way. I asked someone what they thought about this project, and they told me that they would not do a project that took so long and was so complicated and so hard to do. I think that's a compliment because they're highlighting that they wouldn't be able to stick with a project that was this challenging to do, that involved so much work. But I stuck with it. And genuinely, I can't wait to do the next version. Thanks, everyone. Thanks for watching. Wow, I just winged that. I think I did a pretty good job. I'm great. Tonight, we're going to go on a journey together, exploring the past year of my life, designing, manufacturing, and building. Oh shit. Past year of my life, designing, manufacturing, and flying